Here's some notes on the diffusion of gases, such as in the alveoli. There's a diffusion capacity formula, which is as follows. Diffusion is equal to the surface area times the pressure gradient times the gas solubility divided by the product of membrane thickness and the square root of molecular weight. It's helpful to think through each of these factors and how they increase or decrease diffusion. Increasing surface area increases diffusion. Increasing your pressure gradient increases diffusion, and increasing your gas solubility increases diffusion. These are all in the numerator of this equation. Decreasing your membrane thickness increases diffusion, or increasing your membrane thickness decreases diffusion. Decreasing your molecular weight increases diffusion, or increasing your molecular weight decreases diffusion. These are both in the denominator of this top equation. A clinical example can be seen by comparing oxygen and carbon dioxide. Carbon dioxide diffuses 20 times faster than oxygen, and there are two factors to consider when differentiating oxygen and carbon dioxide. Carbon dioxide is much more soluble than oxygen. We saw that solubility was up here, so if you have more solubility, you tend to diffuse faster. Carbon dioxide is so much more soluble than oxygen that it'll diffuse much, much faster. However, carbon dioxide is also larger than oxygen. You can compare their weight in Daltons here. Remember, molecular weight was on the bottom in the denominator. The difference in size between carbon monoxide and oxygen isn't nearly as large as the difference in solubility. So in this case, the solubility wins out and carbon dioxide diffuses faster than oxygen. There are some clinical implications. In emphysema, you have decreased surface area, which will lead to a decrease in diffusion. In chronic bronchitis, you have increased membrane thickness, which will lead to a decrease in diffusion. There are no lung diseases that are compatible with life that can prevent carbon dioxide diffusion. This is like a major requirement for people to survive. You need normal pressure gradients, like an alveolar PO2 of around 100 and a venous blood PO2 of around 40, and you can subtract these to get a pressure gradient of 60, which drives oxygen diffusion into the capillaries. So that would be this part of the equation, the pressure gradient part of the equation.